Great day, everyone! We are Team Holmium, and for today, we are going to tackle the introduction to thermodynamics. So sit tight and let's begin. As for our topic outline, we'll review the principles and ideas behind thermodynamics in the nature of energy and energy changes in chemical reaction segment, to be followed by the introduction to thermodynamics and its application in calorimetry, enthalpy in chemical reactions, entropy, and lastly, gives free energy. What's the first thing that comes to your mind when you hear the word energy? Well, energy is usually defined as the capacity to do work. This definition is not equally significant in chemistry as it is in physics, because not all forms of energy are relevant to chemistry. Tidal waves, for example, can be harnessed for useful work, but the relationship with chemistry is minimal. Chemists define work as directed energy change resulting from a process, with kinetic energy being of particular interest. Other forms of energy include radiant, thermal, chemical, and potential energy. Kinetic energy is the energy produced by a moving object. Potential energy refers to the energy available due to an object's position, such as a rock at the top of a cliff, having more potential energy, and a larger splash when falling into water. Chemical energy, a potential energy, is linked to the atom's position and arrangement within a substance. It is stored with structural units determined by atom type and arrangement, and is released, stored, or converted during chemical reactions. Thermal energy is the energy generated by motion of atoms and molecules in matter, calculated from temperature measurements. The hotter a sample is, the greater its thermal energy. However, it's crucial to differentiate between thermal energy and temperature. For example, a cup of coffee at 708 degrees Celsius has a higher temperature, but more thermal energy stored in warm water. Radiant solar energy, sourced from the sun, is the Earth's primary energy source, causing heat to the atmosphere and Earth's surface, stimulating vegetation growth through photosynthesis, and influencing global climate patterns. Thermochemistry is the study of heat change in chemical reactions. Chemical reactions absorb or release energy, typically in the form of heat. Heat is the transfer of thermal energy between two bodies at different temperatures, often referred to as heat flow. While heat implies energy transfer, we typically refer to it as heat absorbed or heat released to describe the energy changes that occur during the process. To analyze energy changes from chemical reactions, we must first define the system, which is the specific part of the universe of interest. In chemistry, systems typically include substances involved in chemical and physical changes. For example, in an acid-base neutralization experiment, the system might be a beaker with 50 ml of hydrochloric acid and 50 ml of sodium hydroxide. The surroundings are the rest of the universe outside the system. There are three types of systems: open, closed, and isolated. Open systems exchange mass and energy, usually in the form of heat, with their surroundings. For example, an open system with water in an open container can be converted into a closed system by closing the flask to prevent water vapor from escaping or condensing. An isolated system, on the other hand, is formed by placing water in an insulated container, which does not allow mass or energy transfer. Energy cannot be created or destroyed, so any loss of energy must be gained by the surroundings. This process is known as an exothermic reaction, which transfers heat from the system to its surroundings. The endothermic reaction is a process where the system requires heat from its surroundings. Figure 6.3 demonstrates that in exothermic reactions, the total energy of the product is less than the total energy of the reactants due to the heat supplied by the system to the surroundings. Conversely, in endothermic reactions, the difference between the energy of the product and the reactants is equal to the heat supplied to the system.
Thermodynamics is the scientific study of the interconvention of heat and other kinds of energy. With the help of the laws of thermodynamics, energetics and directions of processes can be deeply understood. In this video, we will focus on the first law of thermodynamics. Directly to the first law of thermodynamics, let us first have a brief discussion on what thermodynamics is about. In thermodynamics, the change in the state of a system is studied. A system is a macroscopic part of the universe, and the system interacts with part of the universe which we call the surroundings. There are three types of systems. First, an open system, where matter and energy can transfer from system to surrounding and vice versa. Second, a closed system, which can only transfer energy but not matter. And lastly, an isolated system, where neither matter nor energy can transfer. The system is defined by all of its relevant macroscopic properties including temperature, pressure, energy, and more. These properties are called state functions. State functions are functions which do not depend on the changes that occur during the process. All it focuses on is the initial and the final state. Some examples of state functions are temperature, mass, energy, enthalpy, and entropy. A change in volume can be expressed by the difference of initial and final values of the volume. Path functions are the opposite of state functions. These values depend on changes during the transition from initial to final state of the system. Path functions include heat and work. Now that we are all well oriented with the basics of thermodynamics, let us discuss its first law. The first law of thermodynamics states that energy can be converted from one form to another, but cannot be created or destroyed. While it is not possible to determine the total energy of the universe to validify the first law, we can test its validity by the change of internal energy in a system. Internal energy is composed of kinetic and potential energy. While the total energy of the system cannot be determined, its change can be determined experimentally. When there is an energy change in a system, the surrounding must correspond in equal magnitude but opposite in sign. The change of internal energy of a system is the sum of the heat exchange Q between the system and the surroundings and the work done W on or by the system. Now, let's focus on heat and work. Heat, which is a path function, is described as the thermal energy transferred between two systems at different temperatures that come in contact. Heat can be expressed with the following equation. Another function involved in the change of the internal energy is work. Work, like heat, is a path function. It is the mechanical energy transferred from one system to another. Work can be expressed with the following equation. To understand its concept better, let us try answering this problem. A certain gas expands in volume from 2 liters to 6 liters at constant temperature. Calculate the work done by the gas if it expands against a vacuum and B against a constant pressure of 1.2 atmosphere. To better visualize the problem, here's an illustration of the gas expansion. Let us first solve its expansion against a vacuum. Using the initial and final values of volume, we will get a change in volume of 4 liters. We can use this to determine the amount of work done in the problem. The value of pressure is 0 since it takes place in a vacuum. Inserting the values in the equation of work, we will arrive at a value of 0, which indicates that no work is done in the first condition. Moving on to the next condition, where a constant pressure of 1.2 atmosphere is applied, we will arrive at a numerical value of work. Since the value is at liter atmosphere, we will convert it into joule using the conversion factor 101.3 joule per 1 liter atmosphere. We will arrive at a value of negative 4.9 times 10 raised to 2 joules. Its negative sign indicates that the work is done by the system on the surroundings. To better understand how the sign of heat and work is decided, let us also discuss sign conventions. Work done by the system on the surroundings has a negative sign. On the other hand, work done on the system by the surroundings has a positive sign, indicating gain in mechanical energy. For heat, when it is absorbed by the system from the surrounding, the value will be with a positive sign and is also considered an endothermic process. Lastly, when heat is absorbed by the surrounding from the system, the value will be with a negative sign, which indicates the loss of thermal energy in the system. This is considered an exothermic process. Let us answer this sample problem involving internal energy, heat, and work. The work done when a gas is compressed in a cylinder is 462 joules. During this process, there is a heat transfer of 128 joules from the gas to the surroundings. Calculate the energy change for this process. Using the equation of internal energy, let us insert the values given for heat and work. Since heat is transferred from the system to the surroundings, it will have a negative sign. On the other hand, since work is done on the system by the surrounding, it will have a positive sign. We will arrive at a change in internal energy of 334 joules, and since it is a positive value, the change in internal energy is an increase. Let's have a recap. To test the validity of the first law of thermodynamics, we studied the change in internal energy, which depends on the sum of heat and work. Both heat and work are considered path functions, as they mainly depend on the changes during the process. They are not properties, but are rather manifested during a change. Heat changes in physical and chemical processes can be measured. Calorimetry tackles how this can be done. Calorimetry is the measurement of heat changes during a physical or chemical process. Before we discuss the types of calorimetry, let us first get acquainted with specific heat and heat capacity. Specific heat is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. With that said, its unit is joules per gram degree Celsius. Each substance have a different value of specific heat, which can be seen in this table. Heat capacity, on the other hand, is the amount of heat required to raise the temperature of a given quantity of the substance by 1 degree Celsius. Since its quantity is not per gram, the units for heat capacity is joules per degree Celsius. The relationship of heat capacity and specific heat is expressed by the equation below, where C, heat capacity, is equal to the product of mass and specific heat. Here are useful equations in measuring the heat change. In the first equation, specific heat S and mass is used along with change in temperature delta G. On the other hand, the second equation uses heat capacity multiplied with the change in temperature. The change in temperature is determined by the difference in its initial and final values. Let us now move on to the types of calorimetry. First, we have a constant volume calorimetry. From the name itself, no change in volume will be observed in this process. A known mass of a compound in a steel container, called a constant volume bomb calorimeter, which is filled with oxygen at about 30 atmosphere of pressure, the closed bomb is immersed in a known amount of water. The sample is ignited electrically, and the heat produced by the combustion reaction can be calculated accurately by recording the rise in the temperature of the water. The heat given off by the sample is absorbed by the water in the bomb. In constant volume calorimetry, it is assumed that no heat loss takes place during the measurements. The heat of combustion can be expressed by the equation below. Let's try solving this sample problem. The molar heat of combustion is asked with the following given values. Using the equation where heat is equal to the product of heat capacity and temperature change, we will obtain a change of 57.66 kilojoule. Since heat of reaction is equal in magnitude but opposite in sign, we have a heat of reaction of negative 57.66 kilojoules. Now, we must use the given mass of naphthalene as the conversion factor and multiply it with the molar mass of naphthalene to get molar heat of combustion. The molar heat of combustion is equal to negative 5.151 times 10 raised to 3 kilojoule per mole. On the other hand, constant pressure calorimetry is used to measure heat change of non-combustion reactions. Since the pressure is constant, the heat change of reaction is equal to the enthalpy change. The equation below expresses the heat change of non-combustion reactions. Let's try solving this problem where the specific heat of lead pellet is asked. Here, product of mass of water, specific heat of water, and temperature change is used to get the heat gained by the water. The heat gained by the water is the heat lost by lead pellet in its opposite sign. Thus, we can manipulate the formula for the specific heat of lead pellet and input the obtained values. We will arrive at a specific heat of 0.150 joule per gram degree Celsius.
The use of internal energy is helpful in determining changes in heat for constant volume systems. However, constant pressure systems are used more often in the laboratory. Enthalpy describes heat changes in constant pressure systems. Enthalpy takes into account all factors including internal energy, pressure, and volume, which are all state functions. Thus, enthalpy is also a state function. The enthalpy of reaction is the difference between the final and initial states of the system. In other words, it is the difference in enthalpy of the products and the reactants. As you may have read earlier, changes in enthalpy manifest as changes in temperature. Heat is transferred from the system to the surroundings in an exothermic reaction, thus enthalpy is negative. Endothermic reactions where heat is transferred from the surroundings to the system have a positive enthalpy. To test if you perfectly understand the concept of enthalpy, pause the video and try to answer this practice problem. Each chemical reaction will have a corresponding change in enthalpy. We write thermochemical equations to relate a balanced chemical equation with the enthalpy change that occurs during the reaction. To write a thermochemical equation, it is important to specify the physical states of the reactants and the products for an easier prediction of the sign of the enthalpy change. The enthalpy of a reaction should be multiplied by a factor n if both sides of the thermochemical equation are also multiplied by a factor of n. The enthalpy of the reverse reaction is equal in magnitude with the enthalpy of the forward reaction, but opposite in sign. One good application of thermochemical equations is Hess's law. This states that the enthalpy change of a specific reaction remains the same whether it occurs in a single step or a series of steps. For this practice problem, we are tasked to calculate the enthalpy change for the reaction given on your screen. To solve this problem, we must first take note of the target equation as shown above the given equations. And so, as you can see, we need 3 moles of CO2 and 4 moles of H2O in the liquid state for the products. You can see here that we only have 1 mole of CO2 given, and so what we need to do is to multiply that by 3. So we will have 3 carbons, 3 O2 molecules, and 3 CO2 molecules. We will also multiply the enthalpy change by 3, and that will give us negative 1180.5 kilojoules. For the third equation, we have to multiply it by 4. So we can have 4 H2 molecules. 4 times 1/2 is equal to 2 O2 molecules and 4 liquid H2O molecules. We must also multiply the enthalpy change by 4, and that will give us negative 1143.2 kilojoules. Now we have to cancel all terms that cancel each other out. For the first term, we can cancel this solid carbon here and this one. We can also cancel the H2 molecules from the first equation and the third equation, and that will lead us to C3H8 plus 3 plus 2 is equal to 5O2, 3CO2 plus 4H2O, which is exactly the same as our target equation. Now we have to add all of these values to get the total enthalpy change, and that will give us negative 2 to 20 kilojoules. As defined earlier, internal energy, pressure, and volume are taken into account when solving for enthalpy. To compute for change in enthalpy, we consider the change in all the factors that make up enthalpy. U, P, and V are state functions, so we can compute for changes in U, P, and V by finding the difference between their initial and final states. According to the ideal gas law, PV is equal to nRT. Inserting this expression into the equation, we will have delta H equals to the internal energy plus the change in moles of the gas times RT. Absolute values of U cannot be determined. Hence, absolute values of enthalpy also cannot be determined. But how do we have values of H for different substances? Enthalpy values of different substances are measured relative to a reference value, which is the enthalpy of a substance's standard state. The standard state is the most stable form of a substance at 1 atmosphere. As with any reaction, there is an enthalpy change associated with the formation of a compound from its elements. The standard enthalpy of formation of an element at its standard state is 0. The enthalpy change associated with a reaction occurring at 1 atmosphere is the standard enthalpy of reaction. The standard enthalpy of formation can be calculated by subtracting the standard enthalpy of the reactants from the standard enthalpy of the products. For this problem, we are tasked to calculate for the enthalpy change of the reaction given below. To solve for this one, we have to write the equation for calculating enthalpy changes. We have delta H of the products minus delta H of the reactants. So we have 3 times the delta H of H2O plus 2 times the delta H of CO2 minus the 3 times delta H of O2 plus 1 times the delta H of C2H5OH. Substituting the values that are given on the table in front of your screens, we have 3 times delta F of H2O in the liquid form, negative 285.83 plus 2 times negative 393.5 minus 3 times 0 because O2 is at the standard state plus 1 times negative 277.7. For the enthalpy of the products, we have negative 1644.5 minus the enthalpy of the reactants, which is...
Now we are on our last part of the video, which will discuss about Gibbs free energy. So without further ado, let's begin. So for free energy, which is denoted by the letter G, it is the free energy for a system to do useful work. This is also used as a criteria for spontaneity of a certain reaction, which we will focus on later. So this is often defined with the relationship of delta H, or enthalpy, and delta S, or entropy, at a constant temperature, which is denoted by the formula presented here. So you got delta G is equals to delta H minus T times delta S for a constant temperature process. So if you want to remember this formula, just keep in mind the word agathas. So agathas. So agathas is the formula that you want to remember for relationship of Gibbs free energy with entropy and enthalpy. So later on, you will see more of this one. So with standard free energy change, or the delta G naught, this is similar to those with standard enthalpy that was discussed earlier, to which given Gibbs free energy occurs when reactants are in standard states. So for a short review of the standard states for different conditions, is presented in this slide. So for gases, we have 1 atm pressure or 1 atmosphere. For solutions, it is in 1 molar concentration, while temperature is in 25 degrees Celsius or 298 Kelvin. So do keep in mind that in these computations, we opted to use Kelvin as our unit for temperature. So you will know that if it's in standard state, if we have a short superscript after our thermodynamic quantities, so indicated by this knot here. So given these two formula, these two relates two different concepts. So first is the agathas only in standard state. So the discussion with our agathas same applies to here. While the second one, this describes the um, standard free energy change when we are given the standard free energy of formation in a certain reaction. So as similar to those standard enthalpy of formation, standard entropy of formation, this is also the same. So you're just going to get the summation of all the delta G naught of formation of the products minus the reactants. So that's as simple as it can be. So as for the criterion for spontaneity, it is summarized in this table right here. All you need to know is that having a negative delta G means a spontaneous reaction, while a delta G, which is equal to 0, this means that the reaction is in equilibrium, which will be featured later on. And delta G, which is positive delta G, means that the reaction is non-spontaneous. So do keep in mind that negative is spontaneous, positive is non-spontaneous, and 0 is equilibrium. So that is how you should remember. So with that, let's have a short practice problem. So for this practice problem, you may opted to pause the video if you need more time. Okay, so the question asks, what is the standard free energy change or delta G naught for the following reaction at 25 degrees Celsius? Is the reaction spontaneous or not? So given a reaction here, also the standard enthalpy and standard entropy values for the reaction is also indicated. So you may want to pause. So I'll be showing the answer in 3, 2, 1. Okay. So given here is the solution to the problem. So we are going to use the Agatha's formula. So which is delta G naught is equals to delta H naught minus T times delta S naught. So Agatha's. So just substituting the values, you get negative 9.18 kilojoule minus 298 Kelvin times negative 0.197 kilojoule per Kelvin. So plugging them in our calculator, you will get negative 33.1 kilojoule. So is the reaction spontaneous or not? So as we can see that the answer is negative, this means that the reaction is spontaneous. Okay. So now for our discussion for free energy and equilibrium. So let's give you a short review about the constants presented here. So Q, or the reaction quotient, is the initial value of concentration. So this means that before the reaction goes into equilibrium, we are going to consider the initial values or the beginning values of the concentration of concentrations of the reactants for the reaction quotient or Q. If we're talking about the equilibrium constant, we are going to use the concentrations at equilibrium for the reactants. Okay? So to differentiate these two, let's use the formulas below. So if we're talking about a certain reaction before it goes equilibrium, we are going to use this first one. So delta G is equals to delta G naught plus RT ln of Q. So do keep in mind that delta G is different from delta G naught. Okay. So with this, we are relating the gives free energy with our reaction quotient. So if let's say if we're going to solve for K or the equilibrium constant, we do know that at equilibrium, delta G is equal to 0. So this means that we are going to transpose this expression to the other side. So it will become this one. So delta G naught is equal to negative RT ln of K. Denote the change of Q to K. So if we're going to use this equation if we're talking about a certain reaction at equilibrium. Okay, so these are the two formulas to keep in mind when we're talking about free energy and equilibrium. And now let's talk about the spontaneity and temperature change. So we know that the standard enthalpy and standard entropy values are based at standard states, which are at 180 m and 25 degrees Celsius. So let's say we want to get the delta G naught of a certain reaction at a given temperature. So let's say 1000 degrees Celsius. So by using the standard or the delta H naught and delta S naught of the given reaction, we're just going at 25 degrees Celsius, so substituting it here, while the temperature will be changed to 1000 degrees Celsius. Of course, convert these temperature values into Kelvin. And then just compute. So Agatha's to get the delta G naught at a certain temperature. Why is it like that? Because delta G naught heavily relies on the change in temp or on the influence of temperature. So if we're going to change the temperature, it will also change the delta G naught. So we will talk about it more using this table here. So with this one, it talks about how the spontaneity occurs at certain conditions of temperature. So let's say we have a negative enthalpy, positive entropy. Substituting it here, most likely you will get a negative G. So this means that, again, negative delta G naught or negative delta G means a spontaneous reaction at all temperatures. If we're going to switch the signs, so positive H, negative S, so it will result into a positive G. This means, again, positive, you will have a non-spontaneous at all temperatures. So for this last two, this is how I tend to remember. So if we're going to have two negatives, negative H, negative S, you will have a spontaneous reaction at low temperature, or this means temperatures that are lower the given temperature in the problem. So I normally would focus on the first statement. So of course, if we're going to relate it at high temperature, it will be the opposite. So do keep that in mind. So if we're going to focus on the positives, two positive, so positive H, positive S, whatever you will get for delta G, you would take note that having two positive H, positive S would have a non-spontaneous at low temperature. Or this means it will be non-spontaneous at any temperature lower than the given temperature indicated. Okay, so that is how you would tackle this table in the future. Okay, just do keep in mind that negative mostly denotes spontaneous reactions. Positive normally denotes non-spontaneous. Okay, so that concludes our video for today. So today we ran through different thermodynamic laws such as first, second, and third law of thermodynamics. We've also talked about different thermodynamic quantities such as the application of work, heat, and then the identification of state and path functions, the quantities such as internal energy, entropy, enthalpy, and Gibbs free energy, and how these different quantities were able to describe the spontaneity of a certain reaction. And with that, that concludes for our video for today. For any additional references, you may refer to General Chemistry by Chang, Goldsby, or you can refer to General Chemistry by Ebbings and Gammon.